we are interested in fundamental aspects of crystallization and deformation in polymers. Our work has a very tight relation to the real application of materials. As we know, for example, polymers always crystallizes partly during the cooling down from the molten state during processing. And they crystallizes only in the metal-stable state. And therefore, it is very important to control the crystallization process in order to tailor specific structures to fit specific applications.
We study a new family of polyethylenes, so this is one of the most studied polymers in polymer physics. But in the chain of polyethylene, we can introduce some defects in a regular and controlled way, and we look how the presence of these defects can actually alternate the polymer crystallization process and affect the mechanisms of crystallization.
By using the scattering properties of X-rays, it is possible to efficiently study the structure of the most complex polymer systems. SAXS, small and wide-angle X-ray scattering, is a non-destructive technique that provides structural information on materials from a few hundred nanometers down to the sub-nanometer scale.
SAXS is really a technique that has been around for quite some time now, but it's only quite recent that it's actually been used for looking at two-dimensional structures of polymers. That started in the 90s. And then we've had, of course, in the last few years, we've had an enormous growth in the use of the synchrotron radiation, doing SAXS on polymers and gaining a lot of insight on both structure and orientation of polymers in the nanoregime.
The SAXS technique can be combined with wax to provide simultaneous information on both the nanostructure of the polymer by SAXS and its crystalline phase by wax.
Polymers are extremely complex objects. When they undergo the process of structure formation, the structure can be formed on very different spatial scales, starting from the unit cell, so at the scale of several angstroms, and going to the scale of, let's say, macro objects, such as, for example, polymer spherulites. So it's extremely important to address the structure at the very different spatial scales, and this cannot be done in only one angular range, and for this reason people are typically combining diffraction in wide angles and scattering in small angles, because they can detect simultaneously the structure development on very different spatial scales.
Having access to that nanostructure with the SAXS and that crystalline phase with the wax is a key point for the study of many materials and polymers especially. The other advantage of having access to that SAXS and wax at the same time is that this is opening the possibility to measure again the structure of your materials at multi-scale but under changing conditions. You can apply, like for example, a temperature cycle on your polymer, looking at phase transition on at the nanoscale and at the crystalline phase, and at the same time.
Based on many years of experience and key proprietary technologies, Xenox offers a comprehensive range of laboratory SAXS wax systems. For more information about what SAXS can do in polymer science and about Xenox solutions, please contact Xenox at sales@xenox.com.